In this video, we are going to learn how to find the circulation and flux of a vector field F defined in the domain D and how to use Green's theorem to calculate these values using double integral. So F is the vector field whose components are m and n. It's defined in this domain D. D is open and simply connected, and it's bounded by this curve C, which is piecewise smooth, simply connected, and oriented counterclockwise. Alright, so what's the circulation? Circulation of this vector field around the curve is given by this formula. Integral of m dx plus n dy along this curve C, which is bounding this region D. Okay, and flux of this field F is given by the formula m dy minus n dx integrated over this closed curve C. Now Green's theorem says that we can find these values by the double integrals instead of integrating these functions over the closed curve C. So how do we do that? So we change this integral over the closed curve C to the integral over the domain this curve is bounding, and we replace the function inside by taking partial derivative of the second component of vector field with respect to x and then subtracting partial derivative of first component of the vector field F with respect to y, and then integrate with respect to dy or dx or dy. The order of integration here doesn't matter. Similarly, to find the flux, we can calculate the double integral of this function over this region D. So what is this function? This is partial derivative of the first component of the vector field F with respect to x plus partial derivative of the second component of the vector field F with respect to y. So what does this function represent? This is the circulation density, which represents flow in the tangential direction to the curve. This function is the flux density. It represents flow in the normal direction to this region. Okay, so Green's theorem basically says that circulation and flux can be calculated by using both of these formulas. Alright, so we are going to verify that for this field, given field F, whose components are m and n. M is equal to minus x square y and n is equal to xy square. So the given domain is the region bounded by this circle of radius a, and the boundary is the circle C. The parametric equation of this circle bounding the region D is a cos ti plus a sin tj, where t varies between 0 and 2 pi. Alright, so we write the x and y components, the value of x and y in the parametric form. For any point in this region, x and y, the parametric curves will be x equal to a cos t and y equal to a sin t, where x and y are the points on the boundary of this curve. So we calculate dx and dy in terms of t. Now we find m and n in terms of this parameter t. Why do we do that? Because we want to find the circulation using this formula. It's an integral along the closed curve C, so we need to convert everything in terms of the parameter t and substitute all these values in this formula. So let's see what we get. So the left hand side here becomes, we substitute these values for m, n, dx and dy. Okay, so this is m in terms of t, this is n in terms of t, this is dx and dy. So substituting all these values here, we get this function. Okay, so since we are moving along the closed curve C, the parameter t is going to change from 0 to 2 pi. Alright, so we calculate this integral, which is easy to calculate, and we find that the circulation around the curve is given by pi by 2 into a raised to power 4 using this formula. All right, so now we verify that if we calculate the circulation using this formula, we get the same answer. So for this, let's find out nx and my in terms of x and y. So m is minus x square y and n is xy square. So let's calculate nx. The partial derivative of n with respect to x will be y square. Partial derivative of m with respect to y is minus x square. Okay, so the formula for the circulation using Green's theorem is double integral of nx minus my over this area dA. So this is equal to x square plus y square dy dx. Now what is this domain D? This is the region inside and including the boundary of the circle of radius a. Okay, so now we can calculate this double integral using polar coordinates. So since we are inside a circle of radius a, so the polar coordinates r and theta are going to change from 0 to a and 0 to 2 pi, and the Jacobian will be r. So we integrate this function with respect to r first. We get r raised to power 4 divided by 4. Substitute the limits here, and then we integrate with respect to theta, and we get a raised to power 4 divided by 4 into theta, evaluated from 0 to 2 pi, and we see that we get exactly same answer. So we have verified Green's theorem for this vector field, that circulation can be given by both of these formulas, and we get exactly same answer. Now we are going to calculate flux using this formula and then using this double integral, and verify that Green's theorem is true for this given field. So the flux is the left hand side, the function inside the left hand side integral is m dy minus n dx. So we calculate m dy minus n dx by writing the expression in terms of t for each one of them, because it's integral along a curve, so we use a parametric equation for each one of the functions and each one of the variables. All right, so this function turns out to be equal to a raised to power 4 sine t cos t into cos 2t and dt. All right, now since t is going to change from 0 to 2 pi, it's a parametric variable changing between 0 to 2 pi along the circle. All right, so now we integrate this function, we simplify it using sine and cos formulas, and we find out that integral using this method, integral using this formula is equal to 0. Why is this 0? Because integral of sine 4t is minus cos 4t divided by 4. Now since cos of this angle is to be evaluated at the limits 0 and 2 pi, and it has exactly same value at both of these endpoints, so these terms will cancel out and we'll get 0. Now let's calculate the flux using the double integral formula. So the formula is mx plus ny integrated over this domain D. So we calculate mx, and it is equal to minus 2xy, ny is 2xy. And it's easy to calculate because these terms just add up to give you 0. So the flux is going to be equal to 0. So now we have verified that the flux using both the formulas is the same. So we have verified Green's theorem for this vector field.